Hey guys, how you doing? So welcome to the third video for this series on kinematics. In this video we're going to look at motion graphs. How do graphs represent the motion of objects? Okay, we're going to look at two different types of graphs, a distance or a displacement time graph versus a speed or velocity time graph. Okay, so let's jump into it. Okay, here is the distance time graphs. Yeah, so let's assume that this object is a car and it has traveled from 9 a.m. in the morning all the way to 2 p.m. in the afternoon, and the distance that it has traveled away from home is on the y-axis. Yeah, so it's called a distance time graph because distance is on the y-axis and time is on the x-axis, as it usually is. Right. Now there is some key information that we need to understand on how to read this graph and interpret from the graph, because it tells us some things but it doesn't tell us everything. Okay, so here is what the distance time graph shows. First of all, it shows one-dimensional travel, how far from home the object is. It shows the car's displacement, but what it doesn't tell us is the direction that it has traveled. It only tells us at any given point in time how far from home the car is. We don't know whether the car is going left, right, north, south, east, or west, right? We just know that it has traveled away or it has traveled back home. Okay. Now, you will notice at about 11 a.m. to about 12 p.m. that the object's motion is described by a flat line. Whenever you see a flat line in a distance time graph, it shows that the object is not moving, okay? Because the object is neither gaining or losing speed over time. Gaining or losing distance over time, and therefore it's not moving, okay? Let's have a look and break down how do we figure out some information based on what we have here. Okay, so even though we have the distance and we have the time, if I was to say how far from home the object was at about 10:30, you can probably go to the 10:30 mark here and you can figure out the distance, which roughly will probably be just a little bit over 20 kilometers away from home. If you say what is it at 1:30, it probably will be here at 1:30, and it is about 20 kilometers away from home. Now, not only can you figure out the distance at any given time, you can actually calculate the speed. And so the gradient, which is the slope of the graph, right, will tell you what the speed the object is traveling at on average. Okay, so we represent the gradient by the letter m, and when you calculate speed, speed is simply distance divided by time, and that happens to be the x-axis divided by the y-axis, or in other words, if you take any 2 points in that graph, you can calculate the change by looking at the change in y divided by the change in x, or the rise over the run. Now, how do you do that on the graph? Well, first of all, you need to read the graph from left to right. You never read the graph from right to left because that's silly. You always have to read it from left to right. And so the change in y, if we were to take a look at this first example here, right, the change in y is this difference in height here. So let's take only from 9 a.m. to 11 a.m. The change in y, or the rise, is actually between here and here, and if you look at it, the object has traveled 30 kilometers from 0 kilometers. The change in x, or the run, is 2 hours. It took 2 hours for the car to go from 0 to 30 kilometers, right? Which means if you calculate the slope of the graph, this line here, you can take 30 divided by 2, which will give you 15 kilometers per hour, okay? Now, you will notice there that this line here at 15 kilometers per hour is a shallow line in comparison to this line here, which happens to be quite steep. And you can assume, therefore, that the steep line shows a quicker change in distance over a smaller bracket of time, which means that in this case here, a steep gradient will show a faster speed. So you can see the car has actually gone at 4 different speeds here. It is kind of fairly shallow, 15 kilometers per hour here. It has gone 0 kilometers per hour here along this flat line. It has increased up along this length here, and then it has another one on this way here. Now, the only difference between this line, which is positive gradient, and this line, which is a negative gradient, is that this car is now returning back home here, and whereas it was going further away from home here. Okay, the speed is irrelevant. You don't need to calculate a negative or anything like that. It just simply is an absolute speed, because you can't have a negative speed. Okay. Now, the final thing that you'll never find on a distance time graph is a vertical line. It should not exist, because objects in a vertical line is basically like saying it has changed distance over 0 time. which means it's teleported, which is impossible. Okay, so a vertical line is not possible because it shows teleportation of an object, okay, over 0 time. All right, now here's a bunch of questions that I want you to have a go, so you can hit pause on the video and have a go because I'm about to go through the answers afterwards. All right, so hit pause and give these questions a go, and then we're going to go through them together. All right, cool. So I'm assuming that you have tried to give them a go, and we're going to go through them together. All right, so for question 1 asks, what is the speed the object was traveling from about 12 to 12:30? So from about 12 to 12:30 is this particular bracket here. And once again, you use the gradient to give you the calculations. The rise over the run. So from here to here, the object has gone from 30 kilometers away from home up to 60 kilometers away from home. And it has done that in half an hour, from 12 to 12:30. So it has done that in half an hour. So when we're doing our calculations, you would do 30 kilometers divided by half an hour, which is 0.5 of an hour, which will give you 60 kilometers per hour. So the car, you can see now, is traveling 60 kilometers per hour here, whereas before it was only traveling 15 kilometers per hour here. Okay. Question 2 asks, calculate the speed of the object at 12:30 to 2 p.m. So from this bracket here, right, it has gone from 60 kilometers down to 0, which means it is the distance that is traveled is 60, and that's the rise is 60, and then the run is going to be an hour and a half, which is about 1.5. Okay, now 60 divided by 1.5 will give you about 45 kilometers, and so the car is now traveling at 45 kilometers as opposed to 60. All right. When you do your calculations, you will notice that the rise should actually be negative 60 because it has gone from 60 down to 0, which means it has risen by negative 60 kilometers, right, over 1.5. And so your actual calculation should come up with negative 45, but there's no such thing as a negative speed, so we just ignore that, okay? And it is just 45 kilometers per hour, okay? Question 3 asks, what is the average speed that the object was traveling from 9 to about 12:30? So it wants you to figure out the average speed from here to here, okay? Now, to do that, we then need to consider the total distance covered by the total time. So you actually can just ignore these lines here, and you kind of go, okay, between 9 a.m. to 12:30, the object has traveled 60 kilometers, and it's done so in 1 to 3.5 hours. So you would take 60 kilometers divided by 3.5 hours, which will give you 17.14 kilometers per hour. Question 4 asks you, what is the total distance traveled by the object throughout the whole trip? Now this sounds really complicated, but it is actually really easy because you just look for the peak that the object has traveled. So from 9 a.m. to about 12:30, the object manages to cover 60 kilometers, and then it travels an additional 60 kilometers back home. So in total, the car has traveled 120 kilometers because it's gone 60 kilometers one way and then 60 kilometers back again the other way, giving you 120 kilometers in total distance. All right. So hopefully that part makes sense because we're going to go through the descriptions now. There's a different ways that you can describe motion, right? So when you're asked to calculate certain aspect of the motion, usually you'll use the formulas, the gradient, and etc. But if I asked you describe the object's motion, right, then you need to then use words and sentences or phrases to then describe how the object is traveling. So here are 3 different lines, the green, the red, and the blue, okay? Each of these statements will describe roughly the object's motion over time, okay? So you can see here, both the green and the blue have moved from 0 seconds. So if I was to describe the green object's motion, you would say the object has started at 0 seconds and it has traveled a constant speed, constant increase of 20 meters per second for 5 seconds. You can calculate that by looking at the rise, which is 100, divided by the run, which is 5, giving you 20 meters per second for 5 seconds. The red is very unique because you can see there the red line is curved. It's curved in 2 directions. One, it curves upwards, and the second one, it curves back and tapers off around here. So what you would say is that increasing curve is that the object is actually accelerating. It's not only gaining distance, but it's gaining distance at a faster rate, therefore accelerating up to about kind of the halfway point, in which case it then slowed down and decelerated from about 7 seconds before stopping completely at about 10 seconds there. Yeah, and so you can probably speculate that this is an increase between lights, where the object from the lights at the red light will increase, and then when it encounters the next set of lights, it will slow down again until it stops just before the lights at 10 seconds. Okay, so object started at 2 seconds, accelerated, yeah, then slowed down at about 7 seconds before stopping again at 10 seconds. Right. Now the blue one's quite interesting because you've got 3 different types of motions here. You've got an increase in a steady speed, object stops and doesn't move at all, and then you've got a steady speed and returning back to the start position. So you would say that the object started at 0 seconds, traveled at a constant speed of about 8 meters per second for the first 5 seconds, stops again for about 4 seconds, and then it returns back to its original position after 3 seconds at about 13.3 meters per second. Okay. All right. Speed time graphs. Let's have a look at now a different type of graph describing motion. The speed time graph is like the distance time graph, has time along the x-axis and it has speed along the y-axis. Now, it shows once again a different set of information that you will see in a speed time graph that you won't see in a distance time graph, but it will also give us some of overlapping information. We just need to know how to look for it. Okay. Now, it only shows the changes in speed. Okay. So we don't know the object position at any given time, right, based on just the information shown on this graph here. So what it's saying is that it's tracking the object speed. So after 10 seconds, you will say the object speed is 15 meters per second, right? And then from 10 to 20, the object stays at 15 meters per second, and then it increases in speed or decreases in speed as a result of these changes over time. Okay. Now, once again, the flat line indicates that there is no change, which means from about 10 to about 20 seconds, the object is maintaining speed at 15 meters per second. The object is still moving, which is why it's different from a distance time graph, because in a distance time graph, the object at this point here would not be moving, but in a speed time graph, it's still moving, it's still covering distance, it's just not gaining or losing speed. Okay? What that also means is that the gradient now means something else. It doesn't tell us speed, it tells us acceleration, because acceleration is the change in speed over time, which also happens to be the gradient formula here. So m, which is the rise over the run, or the change in y over the change in x, can be calculated by figuring out what the change in speed is over the time that it takes for that change to happen. Once again, you read the graph from left to right, and in this first quarter or this first section, for example, if we take the first 10 seconds, we can see that the car has gone from 0 speed, in other words, a stationary position, and it has risen to 15 meters per second, and has risen to 15 meters per second over 10 seconds. What that means is that the car has accelerated, and you can calculate that rate of acceleration by dividing 15 meters per second by 10 seconds, giving you an increase in 1.5 meters per second every second, or per second squared. Okay, so you can't confuse the distance time graph gradients from the speed time graphs. You just need to make sure that you understand that they both are representing different information. Okay, now in this graph here, the positive gradient will indicate an object's acceleration, whereas a negative gradient, for example, this one here, will indicate a deceleration. The car is slowing down. So it's still moving in the same direction, but it's just simply moving down at a moving at a lower rate. Okay. A steep gradient will show a fast increase. So this one here will show a fast increase, and a shallow gradient, this one here, will show a slow increase. Either way, it's still moving further away from the original location. Okay. And a vertical line here is still impossible because it's showing an instantaneous change of speed over 0 time, which cannot happen. Okay. All right. Hit pause on the video, have a go at these questions, because I'm going to come back and I'm going to then go through some of these questions. All right. Okay, I just took a coffee break as well. So I'm assuming that you've had a go at these questions, and I'm going to go through each of the questions. So question 1 says, at which stage, A, B, C, or D, of the journey is the object slowing down? So here, you've got A here, B, flat line, C, a shallow gradient, and D, a negative gradient, right? And so remember that a positive gradient shows speeding up, and a negative gradient going downwards shows slowing down. And so the only one that shows a negative gradient here of slowing down is D. Calculate the acceleration of the object between 0 and 10. So we just figure that out. Yeah, you take the rise, so between 0 and 15 meters per second over 10 seconds, and that'll give us 1.5 meters per second squared. Okay, what is the object doing at stage B? So here you can see the object is not increasing or decreasing in speed, but it is maintaining its speed, and it is moving at a constant speed of about 15 meters per second. At what time is the object traveling fastest? Okay, so you got to find the time that the object is moving at the fastest speed. That is actually not as hard as you think. If you look at the graph, at which point in this graph is the speed the highest? Well, at this point, at 25 meters per second, the object is moving at 30 seconds. Okay, so at 30 seconds, the object is traveling the fastest speed. It doesn't stay there for very long. In fact, it's quite instantaneous. It gets all the way to 25, and then it actually slows down straight away after that. Okay, all right. Now, here's an interesting question. Between 10 to 20 seconds, how far has the object traveled? You can see that the graph does not tell you the distance that the object has traveled. You need to calculate that, right? And between 10 and 20 seconds here, we know two pieces of information. One, 10 seconds has gone by, and two, the whole time the object is moving at 15 meters per second. So you can actually calculate it by using the rise and the run, but you're not dividing. This time, if you were to think back to your distance formula, distance is speed times time. Now, speed is actually the rise, and time is actually the run. So if you multiply the speed times the time, or the rise by the run, you will get the distance. So in this case here, 15 meters per second for 10 seconds will give you 15 times 10, and that is actually 150 meters. That happens to be the area under the graph. So if you want to calculate distance, you take the area underneath the graph at those lines, and then you calculate that area of whatever that shape is, and that'll give you the distance that the object has traveled. So you're now applying geometry into the motion graphs. Okay, so at B, the object has traveled 150 meters because that is the area of the rectangle. Yeah, you go length times width, and then you multiply the two together, and that'll give you the distance. Okay, so let's see if we can try and calculate the distance of the area under the entire graph, the total distance traveled by the object. Okay, now if you were to look at A is in the shape of a triangle. So what that means is when you calculate your area, you need to divide it by 2 because the formula for a triangle is a half times base times height. So what that means is if I look at this triangle here, the height is actually 15, the base is 10, and then so 10 times 15 is 150, but you have to divide it by 2 because it's a half for the triangle. So at A, the object has traveled 75 meters. We calculate B, which was 150. C is really interesting because you can see here the shape of C is actually neither a triangle nor a rectangle. It is a trapezium, yeah, which is both a rectangle and a triangle put together. So there's two ways of doing this. If you know the trapezium formula, you can apply to it. It's a half times A plus B times height, right? If you don't know the trapezium formula in geometry, you can simply break the object up into a rectangle and a triangle, and then you calculate each of them separately. So C is pretty much the same as B, so I can infer that is 150 meters there, and I then calculate this little triangle here, which happens to be from 15 to 25 is 10, across 10 seconds is another 10, so that's 100, divided by 2, which is 50. Okay, so the total at C is 200 meters. So this total area here is 200 meters. And then D is a triangle, so I can then calculate that. So that is 25 over times 25. Sorry, 25 times 20, which happens to be, was 25 times 20, to 500. Right, divided by 2 is 250. So the total distance is 75 plus 150 plus 200 plus 250, which should give you 675 meters in total. Okay, so that's really important to be able to calculate, because we use the graph now and we use the application of geometry to calculate distance, whereas we couldn't do that before with the other graph. Okay, so hopefully that makes sense. When we go into the next video, we're going to take a look and change and look at forces and motion instead. But yeah, hopefully that makes sense for you guys, and I'll catch you guys then. All right.